This is section 20.3 called Voltaic Cells, and it's a demo I normally do in class. What we have are two different beakers. I'll kind of draw them here. And one of them has a blue solution of copper 2+, and we put in a strip of zinc metal. The other solution is a clear solution of zinc 2+, and we put in a copper strip. So what happens is we watch it, and what we see is absolutely nothing happens here. Absolutely nothing. We could leave it forever. And think back to chapter 4 for the activity series, and you can actually figure out why that's the answer. But we're going to first talk about Voltaic cells, which is our new topic. It says copper strip and zinc sulfate. I'm going to put right here NR, absolutely no reaction. But if I put that zinc strip into copper sulfate, so remember, I know like this is Gen Chem, but copper sulfate is CuSO42, and really it is a source of copper 2+ ions. So that's a part that sometimes students do not know. Down here is a picture. This is zinc solid, the strip. This blue thing represents a copper 2+ ion in aqueous solution. What happens is a redox process, and that's what we're going to talk about here. As time goes on, what happens is we see this black precipitate forming on the zinc. That black precipitate, when it falls to the bottom of the container, is actually a beautiful copper color. And what it is copper as a solid. I always say nothing up my sleeves. I don't have anything I use. I did not add anything. This is a spontaneous reaction. This is where you have a negative delta G. So, before I go deeper, just about all the chemistry that we know today, it's really come from observations, and many of the observations come from electrochemistry. So if we were doing this in class, we would see that the blue color would actually start to disappear. We would see the copper actually form on the zinc. We would see the copper settle to the bottom. What we couldn't really see is that the zinc solid dissolves, but you could measure that there is zinc 2+ there. So when people talk about voltaic cells, these are the observations they make. They say, the mass of the zinc electrode decreases and the concentration of zinc 2+ ion in solution increases. They would say the mass of the copper electrode increases and the copper 2+ ion concentration decreases. Now again, in limit of time, I'm just going to roar on through. You can slow this down. But what happens is you can deduce what are the two half reactions. If we had copper 2+ originally, a beautiful blue solution, and we started to see copper solid, we would say, hey, that's the half reaction that represents reduction. So we'd have to have an oxidation. So we would see zinc 2+, not see it, we could measure it, and we would see or measure the zinc electrode mass decreased. That is our oxidation process. So building on what we had in the section before, we now have two half reactions. One is an oxidation, one is a reduction, and we have an overall cell reaction. In this beautiful example, we have a 2-electron process, so there's none of that equation balancing to do. It's just really showing you what is a voltaic cell. So here's some definitions. An anode represents the name of one of the electrodes, and it's the electrode where oxidation occurs. And notice both of them start with vowels. I mean, we are a Gen Chem class. We are not like, graduate level, whatever. So let's try to use something that helps us remember. By analogy, the cathode, that'll be the electrode where the reduction occurs, and notice both of them are consonants. So if you're learning it for the first time, this is a good way to get yourself started. I copied and pasted in the equation we had on the previous slide, and what I've done is I've labeled the anode as oxidation. I've labeled the cathode as reduction. It is really important to know these things before we get deeper into the chapter, because deeper in the chapter gives us a much heavier amount to learn. So the last thing to say is if I have a voltaic cell, maybe you will see it on the top hat. it always will have the electrons. They will flow spontaneously from the anode to the cathode. The anode has a negative sign, the cathode has a positive sign. Make another little connection here. Anions are negative, cations are positive. That's another way to help you remember what's happening in this section. Moving a little further, there's some things to say about something called a salt bridge. The salt bridge is this U-shaped tube that is separating those two half-cell reactions. We need to do it because what it does, it completes the electrical circuit. It's just like a flashlight and a battery. The circuit is completed. There's a spontaneous chemical reaction occurring. That spontaneous reaction is actually producing a voltage, okay? So it is there to complete the electrical circuit. It's there to physically separate the half reactions. When we had the demo, which we really didn't have, but if we had the demo, there was no way for us to capture any voltage out of that system. By putting it into two separate compartments, we're able to harness the electrical energy that is produced. Another thing a salt bridge does is it prevents mechanical mixing. And then the thing it looks like they like to ask a lot on the new common midterm, it will provide electroneutrality. What we have is copper 2+ is being reduced. Those ions are going away. We will have the cations migrate from that salt bridge into that cell to replace every copper ion that is reduced. We will also have some nitrate ions, and they will migrate into the anode solution for every zinc 2+ that is formed. I purposely put them into top hat because it's not something I used to stress. I went more for the reaction. I went for the chemistry. But here they talk a lot in the midterms about the salt bridge, and I want you to be prepared. Okay? This next picture, it actually is the same thing in two places. This is very specific. This is very general. Now, many of you, if you're in a STEM field, you'll probably run into some electro processes as you go on. So just think, as you've been sitting in Gen Chem, what you've been looking at here is a zinc solid and a copper 2+. It's all labeled. Where do the ions go? Where's the charge going? Where the electrons are flowing? That is for you to learn to be able to use. But on the right-hand side is the general, where it says that anode occurs in the half cell where there is oxidation. The cathode is in the half cell where there is reduction. These two pictures really are identical. And if you're going to be taking a graduate exam someday, this is the level they're going to be asking you about. They're not going to ask about any of the stuff we described ahead of time. You know, that is your basic background. What they want to know is, do you know how this works? So I'll point out, there we have a salt bridge, but you could also have what they call a porous separator. Again, more terminology, but depending on what you need this for, take the depth that you need. Last slide. This is a short one. There is terminology that we use to describe voltaic cells, and it just reiterates everything that I said at the previous slide. Oxidation occurs at the anode. Reduction occurs at the cathode. Electrons spontaneously flow from the negative anode to the positive cathode. That's because the delta G is negative, and you will soon learn that the E of the cell is positive. All right? The electrical circuit is completed by ions that are moving in solution, and the anions move towards the anode, and the cations move towards the cathode. So the cell compartment needs to be separated by a porous barrier or a salt bridge. I'd say a pretty easy thing to deal with. It's very, very short. What I do have on the bottom is something called a shorthand convention. I will say, here is my zinc 2+ couple. The way I've written it, it's an oxidation, and that denotes that it is the anode. There is this like double line, and that represents a salt bridge or a porous separator. Sitting on the right-hand side, it says copper 2 plus copper. So essentially that represents the cathode, and that is where the reduction occurs. It is much shorter to use the shorthand, no pun intended. Instead of having to write a lot of equations, all you do is write the shorthand. Notice 1 molar solutions. We will soon have the Nernst equation where we will have a Q, and the Q is there when you have any concentration. So everything builds on everything else. The one thing that I wanted to add, if a solid is involved in the half cell reaction, if a solid is in the half cell, what you want to say is that is the electrode. And again, if this is new to you, it probably sounds like a foreign language, but if it's something you've seen before in high school, hopefully hearing it for the second time makes a lot of sense. And I want to add by saying do the homework. Heading into this exam without a lot of practice, very different than 1210. Or better put, couldn't this have happened during 1210 instead of 1220 when the material got a lot harder? 100% behind you. Try your best.